Hello, good morning. Welcome to Comic-Con. And so I'm Harald, I'm CTO, and I'll be walking through our drive to Taco Bell last year. We drove to Taco Bell with one of our openpilot cars in mostly end-to-end system. I'm going to be walking through that and just general stuff that research is working on. So, to start off with, I'm going to just recap some, oh, I got a mouse pointer over there. Let me get that one out. To recap basically what I talked about 2 years ago, which is our general architecture for a self-driving system. So our goal at research is to make a superhuman driving agent, so someone that can drive a car better than a human can. And we have a few particular constraints that we're using to do this. First of all, we want to do it completely end-to-end. So by end-to-end, we mean that we want to put in sensor data into a neural network, so like video and potentially other sensors, but predominantly video, and get driving decisions out and have the system drive. The big reason for this is that this gives more flexibility to the machine learning model to learn behaviors and patterns itself without being constrained by, for example, a perception layer or some kind of other hand-coded stuff in between the system. Secondly, it's really important that we build solutions that scale well with compute. A large part of society is working on constantly improving the amount of compute that is available, and when the next generation computers come out and the next generation's GPUs are ready to train models, you want your system to get better as a result of that. And so end-to-end training is one way to get that because there's no hand-coded constraints, but there are some other things we need too, such as a really good loss function and enough diversity in the data. Diversity of the data we have plenty of users, we have much more than we know what to do with. And then also you need a good simple loss function that reflects good driving. So a clear example of the victory of this strategy is recent improvements in LLMs. They have an extremely simple loss function, a generally quite simple architecture, and they have now demonstrated incredible ability over the last few years. 2 years ago, when I gave this talk, there were still some serious players doing very classical things in self-driving, but honestly today, nobody takes bounding boxes seriously anymore, and everyone is moving to end-to-end type systems. So I just want to end this introduction with a quote from Rich Sutton, who has a very relevant blog post from a few years ago where he described this effect. And he talks of the great power of general purpose methods, methods that continue to scale with increased computation even as the available computation becomes very great. And this was before the LLM revolution, and as you can see, he predicted this very accurately. Okay, so that's kind of the basic overview of what we're trying to build. So we can break this system down into 3 basic parts. First, we have end-to-end lateral control, which is basically just controlling the steering based on the video. End-to-end longitudinal control, which is controlling the gas and the brakes based on the video of the scene. And then the last part is to actually get to the place that you want to go, you need to put in a destination. So humans usually use Google Maps or something like that, and they'll look at the video of that, as well as the road scene to kind of make driving decisions. So that's something we're going to have to do too. And as you can see here, this is how that would work. The model just sees this as well as this, and then it can get you to your destination. Let me open my water bottle here. So, Taco Bell. As a kind of proof of concept of these 3 parts coming together and showing that with an end-to-end system that has no intermediate perception layers, doesn't have any code related to lane lines or traffic lights, can actually do something like drive from point A to point B, we set ourselves a challenge at the beginning of last year, which is driving from downtown-ish, where our old office was, to a local Taco Bell. It contains just some normal diversity of driving maneuvers, like some right turns and some exits, on-ramps, lane changes, all that stuff. And we said we're going to do that by the end of the year without a disengagement, on our device, on a comma 3, just in a normal production car, which was our EV6, and completely open source. So anyone can see what we did. And by the end of 2022. So we got a very reasonable question. Is that going to be an Elon time or real time? But for those who've been following along, it is real time. By the end of 2022, we have posted, the full drive, all the logs, and all the code. So let's go through how we actually did that. So back to those 3 parts. Those are the 3 parts we need to implement, and if they work reasonably well, it will work as a proof of concept, and it will drive us to Taco Bell. So let's start with the end-to-end lateral. This is what the majority of my talk was about last time, talking about the technical challenges involved with doing something end-to-end. What we basically train on is human driving behavior. We train models to predict where humans will drive. We can predict like curvature, yaw rate, or points in space. It's all kind of equivalent. That by itself is not enough to train a system because you need it to be able to recover from noise and deviations and mistakes. So that's why we had to train it in a simulator, and we have to introduce noise and teach it recoveries. And then for this simulator to actually be able to instill behavior in all kinds of driving and to just scale with compute and data, we need to make sure that this simulator reflects the full diversity of the real world. So we constrain ourselves to using a simulator that's based on real data. And we have a method for doing that, which I explained in 2 years ago, which is by augmenting real data to make it seem like you're moving around. And I tried really hard to get a picture where I didn't look stupid from last talk, but that was actually very difficult. So lateral's done. That was 2 years ago. Back then, it was still kind of in alpha mode. People could choose to opt in or not opt in to end-to-end lateral control. They could revert to the lane line policy if they wish. But today, the only thing we ship is the completely end-to-end policy. There's no logic based on lane lines. It just drives based on human behavior. So that's done. So let's talk about the second part, which is end-to-end longitudinal. So when we designed the lateral system, we always had longitudinal in mind. It was obviously never supposed to be designed specifically for lateral, but we were focusing on the challenges involved specifically with lateral first, but always keeping in mind to expand this to longitudinal later. So most of the architecture worked exactly the same for lateral as longitudinal. Instead of it being yaw rates and curvatures that are relevant to predict, you predict speeds and positions and accelerations, but those together with lateral come into like a complete plan of where to be in 3D space. So we can plug this into the simulator that was successful for lateral, but we immediately start to get some issues, which is our simulator was pretty rudimentary. It used, as you can see here, this is how it would work. We would warp the image basically sideways. Essentially, we were assuming that everything in the scene was on the road plane, and we were warping it to be consistent with that. But that means that everything in the background, all the cars kind of warp sideways. And that actually wasn't that big of a problem for lateral because the road is what matters most. But for longitudinal, you can see it's a lot more extreme. So we need to do something about these simulator artifacts. The model can't learn intelligent behavior when there is so much artifacts in the simulation. So this brings us to how do we make the simulator better to basically make the background reproject well when we move around, and also other cars. We have a rudimentary segnet that we use for a variety of things. It predicts a very minimal set of classes, doesn't have any bounding boxes. It just predicts is something part of the road, part of the background, part of your car, or part of other movable things. And you can see that working in this scene right here. So you can quickly start to make some pretty rudimentary assumptions about what these things are and how far away they are, just on what they are. So the road is generally relatively flat and continuously flat and forms some kind of plane. The background often sticks up straight up, and so do most of the cars. So with those assumptions and a very accurate understanding of the road plane, we can actually kind of put in a depth for all these objects based on that, and it won't be super accurate, and especially won't be accurate for things in the background, but the most important things are the things in the immediate background and and the cars on the road. And because we have very good road plane estimation, we can actually do this quite well. So you can see this in action here. So this is what it was on what we trained the lateral models on 2 years ago. And then with the new assumptions, you can see some artifacts here, for example. But the models really see a kind of abstract version of this. And so they capture most of the behavior, especially because things on the road are perfectly reproduced, which are, for all kind of driving, the most important. So we plug that all in. We do the same as lateral. We train some models, make them bigger, try some stuff. And that works. You can see here, this is what we posted around the time we started having successful experiments on our EV6, just coming up to traffic lights. It slows down, speeds up appropriately. And it's also surprisingly human in doing this, despite us not having to hand code any kind of smoothness or controls-related things to achieve that. It just knows from human behavior what a reasonable approach to a stoplight looks like when it's either red or orange or green. So again, this is completely end-to-end. There is no traffic light code that achieves this. This is just learn how to do gas and brakes from human driving. So just a little fun side note on that. There is actually traffic light code in our internal code bases, but it runs this traffic light in our meeting room that we can, over the internet, change colors on. But yeah, so that's the only traffic light code in the comma code base. Everything that makes your car stop at traffic lights is learned end-to-end behavior from machine learning models. So that sounded really easy. I just gave you one quick fix to our simulator, and it went from crappy to a little bit less crappy, and all of a sudden we have something that stops at red lights and stop signs. Now, is it really that easy? Well, no, because it took us 2 years, and also no one else has really done this, so it can't be that easy. So I just want to talk about, even though these ideas are extremely simple, and the solutions are also very simple to the problems we're facing, actually implementing this and developing a shippable system ends up having a lot of challenges and several things that cost a huge amount of time. So the first problem is we build an end-to-end system because it's extremely robust. It can learn driving behaviors even if the ground truth is noisy, even if the ground truth is completely wrong. For example, if we were to just take 1% of the driving images and flip them upside down, the models would still learn to drive. If we were to reverse some of the videos, the models would still learn to drive. But the problem comes in when you start to see regressions in some of the edge cases, and it's not entirely obvious. So you need extremely good tests and infrastructure and tools to understand how good your models are and which things affect it, so that you don't have these little subtle regressions that don't cause obvious failures, but overall regress the performance of the system. And over these years, we've found hundreds and hundreds of these types of bugs that will completely break some tiny percentages of the ground truth. And every time we improve them, everything gets slightly better. Another thing is all these things rely on extremely accurate road plane estimation. So we need to understand the curvature of the road and the pitch of the road and exactly how high the car is above the road and all those things. Without that, you also start to get pretty serious issues. But I think where we spend most of our time is in the code we delete, the things we refactor to make them simpler, and the bad ideas that we try, and then have to reject and completely delete. It's always a continuous fight against complexity. That's what we focus on most on Comma. We want to reduce complexity, keep the solution simple and manageable, because that's how you can have a good chance of finding as many bugs as possible and not being susceptible to this issue where you have this large, robust ML system that we constantly have bugs, give it bugs to, and subtly regress behavior overall. And as a proof that this is a pretty good strategy, we have a really tiny team working on this stuff, and we have a pretty small code base. Yet with that, we've managed to ship end-to-end systems that, as far as I know, no one else has, and especially none that are commercially available. So this is clearly effective. To give you an idea of how tiny the team is, everyone from the research team and infrastructure team, except our newest hire, is giving a presentation today. So that's how small the team really is. So since I spent so little time on what the actual solution was to end-to-end long, because it really was quite simple, I want to give you some ideas on the things that we really did spend time on and that cost a huge amount of time. So first of all, we spent probably over half of last year doing a really big refactor. Now, I'm not going to go into the details of explaining exactly what this refactor means, because the original architecture didn't really make sense to begin with, which is why we had to refactor it. And if I tried to explain it today, I don't think I would understand it myself. But basically, the system that we had shipped to achieve end-to-end lateral planning had many steps. It included student-teacher approaches. It included different types of architecture that worked together, and it had many stages of ground truthing. And it was just difficult to move away from that because it was very effective. It was deployed in the field, and if we wanted to refactor it, we had to make sure that the new, simpler version was just as good. And theoretically, it should have been, but it just took a serious amount of effort and testing and refactoring to get there. But after a little bit over 6 months of work, we managed to do that. We were able to take the training time down from, at the time, around 5 days from beginning to end with all the models we needed to just 2 days. We had 4 models before that needed to be trained, all necessary, that we could reduce to just 2 models. So now it's just a vision model, which takes in scene, compresses it to an intermediate space, and then a policy model that actually makes the driving decisions. And this was somewhere in the middle of last year, or even a little bit before that, and since then, infrastructure improvements and other optimizations have taken this training time down from 2 days to much less than 1 day, and Greg will be talking about that more too. So that's a really big deviation, by the way, from what many other people are training. Training models in 1-2 days is not really that common in machine learning world, but something we feel very strongly about because it allows you to iterate very quickly and correct mistakes very quickly. Whereas if your training run takes 3 weeks, that means, in 1 year you can fix 50 bugs, which is not that great. So that was a positive thing that we spent a lot of time on. There was also some things that we wasted a lot of time on. First one was actually one that seemed like a great idea last Comic-Con, and that we were advertising as something that was going to give good results soon, which is Stoplines. So you can do end-to-end longitudinal by just predicting speed and acceleration, or you can kind of find places that the human stopped and then say this is like a place to stop and try to stop for that place. We already had logic for lead cars that tell us how to stop in a place pretty smoothly, so we thought this would be pretty easy to implement. But in reality, even though it's very easy to predict these places to stop with the model, you end up seeing that not all places to stop are built the same. People stop very decisively for a crosswalk, very decisively for a railroad crossing, not so decisively for a stop sign on an empty road, for example. So the end-to-end is a much better approach here, and as soon as we, even within like 2 weeks of trying to replace the stop line logic with end-to-end, we saw it showed way smoother behavior around these things and way more comfortable. So we probably wasted a few months on that. And then the other thing is Depthnets. So the solution I showed earlier was basically estimating the depth of the road plane for simulation, making some basic assumptions about the background and other cars, and then reprojecting to simulate. And that sounds extremely simple. That sounds like it's too stupid, and really what you should be doing is have a large machine learning model that predicts accurate depth of everything in the scene, and then you won't have all these weird artifacts that I was showing earlier. So that sounded like a good idea to us, and we spent a few months training models that did this, and they did predict depth relatively well, but they were still quite noisy. They weren't as accurate to understand the road plane. Without the assumption that a road plane is flat and continuous, there was a lot of inaccuracies there, and as I mentioned, that's a really critical part. And also in the things that it should have been way better at, like the background, you start to see these halos around stuff in depth. And then beyond that, you start to even get more issues, which is what's the depth of the light that comes out of a lantern? I mean, there's no real answer to that. The depth of a pixel isn't necessarily a real concept. It makes sense in many cases, but as soon as you start talking about shadows and reflections and all that sort of stuff, it breaks down. And when we were doing stuff with Depthnets, we actually were finding a lot of issues related to lighting that were causing problems in the other approach. So we weren't even going to fix those with the Depthnets. So after a few months of that, we completely abandoned this approach. So that's end-to-end longitudinal done. As you can see, it was mostly bug fixes, mostly little cleanup. There was hundreds of bugs that we fixed that I didn't talk about, and then some big stuff like these refactors, and then just the slightly improved simulator. And that's what produces the end-to-end longitudinal behavior that we ship today in experimental mode. So that's done. And then the third part, which is we have to actually put the map into the model. The idea here is extremely basic, which is we have some video of navigation feed, just like Google Maps. We show it to the model, and the model can understand which driving actions to make by seeing which the humans made to get to a certain place. Mitchell's got a whole talk about this later, and about the challenges in testing and actually shipping something like that. And as of 2 days ago, we released end-to-end navigation as part of experimental mode. So that's also done. So now we're starting to get pretty close to having something that we think we can try this Taco Bell attempt on. There's a couple more things that we ended up doing. So we've got the model here. That's basically what I've been talking about so far. We have some other controls stages. What we call a planner is essentially a controls layer. And that needed some changes to accommodate high angle rate turns and 90-degree turns. That's in release. That's not in the state that was necessary. Another thing we did is we conditioned the model on aggressiveness of drivers. So the idea was if we classify every driver as either being smooth and conservative or aggressive, we can also tell the model at runtime to drive like a conservative driver or like an aggressive driver. And we did that for the Taco Bell run so that it would drive more like a conservative driver and go slower through the turns and just generally be more comfortable. And then the last thing is we did map-based lane changes. So the lane changes are completely end-to-end. We just say do like a human would, but to trigger the lane changes, we used the Mapbox logic that said in which lane to be and if there's an exit coming up. So that's just 4 commits. That code is still open. You can go look at that code. The logs of the drive are public, and the models are end-to-end as we intended, and there's only a couple other things that we had to change. And so December 15th, we ordered our food from Taco Bell and completed our challenge. So I'm just going to play the video here for a second. I'm going to attempt to speed this up, which is very high risk. Okay, that went pretty well. So as you can see, it starts in the city. There's some just some normal stop-and-go traffic with some traffic lights that it does fine and does the on-ramp here. Then there's a short section on the highway, so you can see that lane change it made there was based on the map-based logic. So OpenStreetMap said you're on the on-ramp, so switch into the lane, and then same here. There's an exit coming up, make some lane changes to the right. Yeah, and then there's just a few minutes on the highway, take the off-ramp. There's some turns here, and I think there's just a final turn coming up, and then we'll see Taco Bell in the view. So just this left turn, and then Taco Bell should be right there, somewhere. Oh, there we go. Right, so that was our... Thank you, thank you. So that was a demo. We make fun of demos a lot because there's a massive difference between shipping something and having a demo of something. And the Taco Bell drive was a demo. Like I said earlier, we wanted a proof of concept of the systems that we intend to ship working together. But that's only the beginning. We then still have to go through the effort of making this stuff actually usable and comfortable and reliable, and that's way more work beyond the demo. So I think we did maybe about a dozen drives, I think, once we had the models that we wanted and all the end parts. There's a whole bunch of reasons why we redid drives. Sometimes we had camera issues. Sometimes openpilot was too slow. Sometimes openpilot didn't take the exit. And actually, I think about 30% of our drives were unusable because there was a whole bunch of trash on the on-ramp that some car dropped. And that was about 4 drives ruined until we waited for the city crew to clean it up. But yeah, so it did it, it can do it, it's end-to-end, but there's still work to be done. So when will it actually be good? So we have experimental mode, people can use end-to-end long. It's about 22% of people that use it today. And it still has flaws, but some people prefer driving with it. So if we look back at the situation of end-to-end lateral control, we can go back 2 years. I found this message in our Slack, Adib saying we have 16 point a lot of numbers of people who were using laneless at the time. And currently, we're already higher for end-to-end long. So that's pretty promising. What you can also see in this image is how our metrics changed over 2 years, from Slack messages to a real dashboard and something that we can track over time. So some interesting things to point out. End-to-end longitudinal is very relevant at low speeds, and you can see here that the engagement numbers are significantly higher at the lower and mid speeds than without end-to-end longitudinal. But then on the highway, there's still stuff that we're trying to improve. If the model decides to drive too slow, people will generally disengage and drive faster. So that's one of the things that we're working on fixing for end-to-end long. So this engagement minutes is a bit higher than it is for normal driving. Normally, it's about 25 to 27%. And in miles, I think now we're hitting about 55 to 60% of miles are engaged of openpilot users. So that the majority of our users driving is driven by openpilot. And then that's 2 of the 3 parts. And then the third part is navigation, which is released 2 days ago. So when will it be good? Well, if the past is anything to go by, which it should be, then in the next 2 years, we'll be getting these numbers to 100%, and all cars will be driving to Taco Bell. Thank you. So that's what we've done so far. I'm going to talk a few quick notes about what we're working on next. So we keep talking about end-to-end. We even have hats that say end-to-end. And end-to-end machine learning is really the core of what research stands for. We want the models to do as much as possible, internally, to make everything as simple as possible, and have all the difficulty be dealt with by the gradient descent of the model training. This is an extremely effective strategy, and the last few years have really driven this point home with things like GPT-4. So we still have a simulator that's hand-coded physics. We estimate the depth with some rudimentary assumptions. We reproject. That's not great. We want to have machine learning models that can simulate for us. That's something that Yassine will be talking about later. We still have classical controls. The controls is quite smart and does a lot of learning, which Vivek will be talking about later. But it's not machine learning. So that's something that we can improve. Eventually, we will need reinforcement learning. It's normal for the model to need to do some driving with your car to get used to it. That's how humans drive too, and should improve over time. So that's something we're looking into. And then finally, a little bit more long-term, every time one of our users disengages, they're giving a signal that they would prefer to drive than openpilot. That's something that we want to feed back on, because that means our system did something uncomfortable or undesirable. And so in the future, we want to feed those signals back directly into training and have the models learn to optimize how to make the people happy. So, and then if we zoom out a little bit more, we can think, what's an even more general and more end-to-end approach than just focusing on driving? So driving is a subset of robotics. There's, ADAS systems are some robotic system. You have even a bit more niche. You have like these self-driving race cars. But there's also just general purpose robotics, and they share a lot of things in common. interacting with the real world, understanding actuators and friction and physical limits. And that's something that, as self-driving systems improve, will become more and more relevant there too. And this at first may seem a bit weird to think like that you can make a more effective system easier with a completely general approach than you can with something hyper-specific. But just to give recent examples again, anyone who's making machine learning models specifically to be a medical doctor or a lawyer is now completely outshined by GPT-4, and nobody that was working on GPT-4 was specifically optimizing for that. They made a general purpose language model, and it beat everything specific. And so it's not unreasonable to think that that's how robotics will play out too. So we want to keep zooming out and thinking, are there general purpose robotics methods that will be very effective in self-driving in the same way as general purpose language models were good at domain specific things too? So along that axis, on stage we've got Billy and Silly. They're a little side project that we've just been working on. The Comma 3 is a great development platform. It has good compute for machine learning. It has a screen, microphone, sensors, kind of everything you need in a robot, very similar to a human head. And the only thing that's missing to do robotics experiments is to put some wheels on it. So we do sell those wheels. It's very much a dev kit, but we've been having fun with it over the weekends to just kind of experiment with some kind of robotics types things and see how well the Comma 3 holds up, and if there's anything interesting we can learn from that. So I think it was a couple weeks ago, some of the research engineers went to a hackathon with Billy and Silly, and they won second place doing just some things with LLMs talking and taking a picture of you and printing it. So more on a little bit of fun robotics with Comma 3. We're going to do a hackathon at the office. There's going to be some kind of indoor navigational challenge. Can we use machine learning to navigate indoors? Is that similar to driving outside? That's the kind of stuff we want to explore. We'll probably have some obstacle course indoors and have people try to get some kind of speed run through that. It's going to be the whole weekend at the end of September. We'll do 20, 30 people. If you want to come, you should apply, and we'll select 20, 30 people from that, and we'll post more details about that later. It's going to be at our office, which is super cool. We moved into a new office last year. It looks a bit like a compound and has a fountain. So if you're interested in a robotics hackathon, definitely check it out. And that was it from me. So let's move over to questions.
All right, I'll be doing some walk-around Q&A. Does anyone have any questions? All right, we'll start up here.
So I was just curious for the navigate on openpilot. I saw that in the video it was doing fully autonomous lane changes, but as far as I'm aware, looking in the code and on my own custom branch, I don't see that it's actually it's only using the blind spot sensors on my Toyota 2020 Toyota Corolla, but it's not using the rearward-facing camera. So if it's only using the blind spot sensor, but the blind spot sensor is not 100% effective.
Right.
So how safe would it be to do those lane changes with just?
So it's still an ADAS system, so you're expected to pay attention any time. So
yeah.
For example, in a Taco Bell drive, you can see that I'm checking the blind spot monitors for those lane changes.
Yeah.
And I mean, that's kind of what we're imagining. And also, this is true for all of openpilot driving for the foreseeable future. Okay. You need to supervise it. So yeah, the expectation is we can make lane changes when we think it's a good idea, but there's still some burden on the user. But
okay.
That aside, in the future, we are going to use both the interior-facing camera and the blind spot monitors to check this. So it should become more reliable when we move to that. But we haven't shipped that yet.
Oh, okay, gotcha. And just one more small question, does that work on because in the DBC file, I don't see lane change or the indicator status. So
yeah, that's going to be car specific, and then the interior facing camera will be on all cars, obviously.
Any other questions down here?
Hi, 2 questions. Did you go to the retreat after you delivered Taco Bell Drive?
So it's planned for October. But it's real.
It's
and
always
happening.
planned for October. And the second question, as far as I understand, the end-to-end long doesn't give anything specific attention to speed limits, right?
No, it doesn't.
So like I'm from Europe, and like I know that here you can make a pretty good guess in states like what the speed limit is going to be. In Europe, it's a mess.
Right. So
Like-
I mean, that's going to change in the future.
Cool.
Just like European users need to pay attention to lane changes to speed limits, openpilot will too, and in the future we'll add that as an input. It's just not the priority right now.
For depth prediction in the simulator, have you considered or tried out using neural radiance fields or anything similar to that before?
So I didn't train the Depthnets. Yassine did those. But just generally speaking, we didn't see a future in that approach. The concept of depth just doesn't scale towards the end. And so even if we had perfect depth nets, we didn't see a solution. So we were actually dealing with a lot of issues, which is, so you've got headlights of your car, they illuminate the road in front of you. And when you start augmenting the video, you need to augment those lights too. And a depth net can never help with that. And that's the real reason why we gave up, not because we were confident, obviously you can get better and better models, but not that we can solve this concept of depth to make a good simulator.
Hi. Is the model trained entirely on simulated data, or is there any fraction of real-world camera data too?
So it's trained entirely on simulated data, but the simulated data is all real video that is augmented.
Okay.
There is no actually simulated, there is no like pure simulation data,
I see.
like Unity or something like that.
Anyone else down here? All right.
Yeah, thank you for the presentation. So, you know, I think a lot of the questions around like, hey, this doesn't seem like it's ready for like general public driving prime time, but this is still quite an impressive system. Are there narrower applications that are now much closer to being kind of production ready?
Twice or?
Yeah, with end-to-end self-driving. So say, for example, you can't drive on a public road, but could you drive around a mining site, for example?
Oh, I mean, I guess, but yeah, we're just not really interested in that. We want to make a really good ADAS system and kind of expand on this robotics AI future, I guess.
Can you talk a little bit more about some of the techniques for the end-to-end nav with the map? Like, for instance, keeping it at like a static zoom level versus zooming in as you get close to turns.
There's a whole presentation about that later this morning, and we'll go into a lot of detail.
Okay.
That's why I glossed over it very quickly.
Okay, I have some more questions, if that's okay. Can you talk about maybe some of the challenges with disengagement analysis for cars that don't have OP long? You know, how do you detect it's a disengagement for just a failure of the stock ACC versus an actual openpilot, you know, long?
I mean, we know whether they're using stock long. So I mean, obviously we know that context when we're looking at the disengagement, right? We know if it's their system or not. So that's not an issue. There's actually some disengagement analysis talk coming also later. I think Wei Xing will give some insight into that as well.
Okay, one more question related to that. You know, is the training data that you should get more useful from cars that have OP long enabled, or you know, do you still use it for cars that don't have OP long enabled that are using the stock ACC?
So training data, the way we train the models now, not necessarily, but as a kind of feedback for us as the engineers to understand how the system is being used and where it's failing, it's more useful when you have OP long. But again, it's not training the models, it's training us, but I don't know, that's kind of the same thing in the end.
Thank you so much, Harald.